Everyone, welcome back to the channel of Principles of Engineering. Previously, we have solved 5 bits manipulation problems in the csapp datalab. Today, we're going to summarize what we have learned so far and introduce 3 common techniques or 3 common tricks we will use when solving bits manipulation problems. Trick number 1: to use a mask to extract the bits we want. We usually use this trick whenever we want to extract a fixed length of bits we want from a number. And also in the mask we use ones to save the bits we want, and use zeros to ignore the bits we don't care. Right? Let's take a look at the examples on the right side here. All these 3 problems are the ones we solved previously in earlier videos. So this get back problem, at the last step here, we use this FF, which is 8 bits of ones here to extract the last 8 bits from the results we got. This is probably the most simple type of mask we will use when solving bits manipulation problems, which is a constant number. In the second problem, the logical shift, the first step is to dynamically generate a mask based on the input n, and then we apply this mask to the other operations of the results from the intermediate results, and then we got the final results, right? So in this example, we start to generate dynamic type of mask based on some input data, and then the last example here is similar to the second one. In bitcom problem, every iterations of the calculation here, we dynamically generate some mask even based from the previous mask, and we apply to that to the intermediate results in order to get the result we want from each step. So to summarize, in all these 3 examples here, we use some form of a mask to extract the information or the bits we want. We use ones to save the bits we want, and then we use zeros to discard or to ignore the bits that we don't care about. Okay. Trick number 2, we use parallelism to reduce the number of compute needed. What do I mean by this? Suppose we have 2 numbers, a which is a 32 bits number. Let's say this is 32 bits. And then we have another number which is also 32 bits number. And we want to, let's say, do some operation between A and B. And let's assume we want to add these 2 numbers. We only care about the last bit of the result. Even if we only care about the last bit of the result of this add operation, but the CPU will always take the entire 32 bits of A and B and add them together. Every time, even if we only care about the last bits, the rest of the bits, they are still being computed in one single operation from the CPU. To better understand this, let's take a look at the example on the right side. These are the 2 problems we solved from previous videos as well. In the first example, bit count, what we try to achieve here is to check and calculate the number of ones in the 32 bits integer. We talk about using a naive way of checking the last bit of this input number x, and then shift the number x to the right by one position every time, and then we accumulate that whether it has ones in the last bit or not, and then return the result. This naive approach can work, but we need to do this same operation 32 times for this entire 32 bits integer. In order to reduce the number of calculation, what we did in the earlier video was to construct the mask in a way that it helps us to not only add up the number of ones in the last bits, but we do that in different positions of the input number at every time when we do this operation. And these techniques enable us to reduce the total number of iterations from 32 to, let's say, 1, 2, 3, 4, 5 iterations. In the second example, the bound, to solve this problem, we need to check whether there's any ones in any of the 32 bits position of the input number x. To do that, again, naively, we can still check the last bit every time and then iterate this by 32 times, but that will exceed the maximum number of operations. And then again, we can leverage this parallelism mechanism. Every time we check not only one bit, but we check like 16 bits here in the first iteration, and the next time we check 8 bits, and the next time we check 4 bits, right? So in total, we reduce the iterations from 32 to, again, 1, 2, 3, 4, 5 iterations for these 32 bits. So these two examples share this common idea of reducing some operations, some type of iterations from 32 times to 5 times. So this concludes how to use the parallelism to reduce number of compute when we solve bit manipulation problems. Trick number 3. Use OR to preserve ones, and complementary use ANDs to preserve zeros. Let's take a look at the example on the right side, which is the same as the previous slide. In the bound problem, the core part of the issue is to check whether there's any one in this input number x. And to do that, we heavily leverage this OR operation in each of the steps here. This technique seems to be easy and obvious, but I just want to put it here to remind us that it's very easy to forget about this important trick, especially when we are under pressure. I see this happen a lot when people interview with companies, that they are too nervous and they just simply forgot about this easy trick here. So with that, we have seen all the 3 common tricks I want to talk about here in this video. And here's a table that summarizes the 3 tricks we talked about just now. Hope you enjoyed this video and learned something from this. I'll see you next time.